Good morning, dear students. Let's continue the topic electromagnetic induction. Okay, up to the previous class, we have studied the Faraday's law, Lenz's law, and energy consideration. Okay, of the motional EMF. In the today's class, let's continue regarding the eddy current. Okay, how we can define the term eddy current? So, eddy current are the induced currents on the bulk pieces of conductors when they are subjected to the changing magnetic flux. Okay, the flow of patterns of these currents resembles the swirling of eddies in water, and so they are called eddy currents. Swirling means, for example, when you drop a stone, you can see a ring like structure, swirl like structure. Okay, so that type of structure, flow of current, can be seen on the surface of the conductor when these conductors are allowed to move in the uniform magnetic field. Okay, so they are discovered by the Foucault in 1895. Okay, eddy, so eddy current is also called as Foucault current. Okay, so here eddy currents are basically current induced on the body of the conductor due to the change in the flux linked with the conductor. Okay, due to change in the flux linked with the conductor. So in this picture you can see when this pendulum, that is rectangular conductor, has been suspended in a uniform magnetic field, that is in between the north and south pole of the magnet. Okay, so what happens, you can see oscillation occurs, you can see the flow of current in the on the surface of the conductor. So when it comes inside, direction will be one, that is direction of current on the surface will be in one direction. When it moves away from the magnetic field, the current direction on the conductor will be opposite to the previous one. Okay, so let's see an experiment, that is, okay, you can see here the metallic plate is suspended between the two poles, that is north and south pole of the electromagnet as shown in this figure. Okay, it is allowed to come to rest when it is plane is perpendicular to magnetic field. Okay, its plane is perpendicular to the magnetic field, then the metal plate comes to rest. First, initially, if the magnetic field is off, okay, in the absence of magnetic field, what we can see, the metallic plate is allowed to oscillate, and it is found that it oscillates for a long time. Okay, what happens if there is a magnetic field? Okay, magnetic field, that is electromagnet is switched on, then plate is set to oscillate. It is found that plate stops oscillating and comes to rest quickly. What happens when the metal plate is subjected to the uniform magnetic field? It oscillates, but its oscillation stops or comes to rest very quickly. Okay, so when the electromagnet is switched on, the plate oscillates in a strong magnetic field. Okay, because of which reason? Because of continuous change in the magnetic flux linked with the current. Okay, when the plate oscillates in the in the field, magnetic field, what happens? The magnetic flux linked on the surface of the conductor keeps on changing. Okay, so the current will be generated on the surface of the conductor. That current is nothing but a eddy current. Okay, so here eddy current always tends to oppose the motion of the plate. Okay, so if it oscillates, it tends to stop the oscillation of the plate, and finally it brings to the rest condition. So the kind of opposition offered by the eddy current due to the motion of the system is called as what? Electromagnetic damping. Okay, so when a metal plate is subjected in the magnetic field or the in electromagnet, So plate oscillates on the surface due to continuous change in the magnetic flux. Okay, when it oscillates, the eddy current will be produced on the surface of the plate. So eddy current opposes the motion of the plate, and what happens, it finally bring to the rest condition. Okay, so this phenomenon finally called as what, electromagnetic damping. Okay, next, suppose if there are number of holes or the slits, you can see here there is no complete metallic plate. Okay, complete one rectangular structure, you can see the fork like structure, isn't it? If we replace the complete plain metal plate into this fork like structure, so it reduces the area available for the eddy current. Okay, so we can reduce the damping effect. So if we reduce the damping effect, what we can say, the plate oscillates very freely. Okay, next, so eddy current arises some drawbacks or disadvantages. Let's see. The production of eddy current in a metallic block leads to the loss of electric energy in the form of heat. So eddy current forms on the surface, very much heat will be produced on the surface. Okay, so here heat produced due to, second one, heat produced due to eddy current breaks the insulation used in the electrical machines or appliances. Okay, the amount of heat produced will be in such a large quantity that it breaks the insulation of the machines or the appliance. Okay, next, eddy current may cause unwanted damping effect. We require the oscillation, but immediately that oscillation comes to rest. Okay, these are the some drawbacks or the disadvantages of eddy current. So not only disadvantages, there are certain applications or the eddy current advantages which are we are using the many purpose. Okay, so let's see the magnetic braking in trains. Okay, one of the application here, strong electromagnets are situated above the rails in some electrically powered trains. Okay, electric powered trains, when the electromagnets are activated, the eddy currents are induced in the rails and oppose the motion of the train. As there are no mechanical linkages, the braking effect will be smooth. Okay, so what happens, the electromagnets which are situated at the wheels of that, when we uh, when the magnets are activated, what happens, so braking effect will be very smooth. Okay, so the eddy current will be produced on the wheels. Okay, next, electromagnetic damping. So the practical purpose, which type of galvanometer we will use. Okay, so that current will be of eddy current, and the which type of damping will be there, electromagnetic damping. Okay, certain galvanometers have a fixed core of non-magnetic metallic material. When the coil oscillates, okay, the eddy currents are generated in the core and oppose the motion of and bring the coil rest quickly. So in the galvanometer, when currents start to deflect, immediately the galvanometer comes to rest condition, that is because of the eddy current. Okay, next example, induction furnace. Okay, here induction furnace are used to produce high temperatures and can be utilized to prepare alloys by melting the constituent metals. If there are heavy metals, by melting that we can obtain the alloys. Okay, when a high frequency alternating current is passed through a coil which surrounds the metals to be melted. Okay, so eddy currents generated in the metals produce high temperature and sufficient to melt it. Okay, so when these metals are present in the furnace, what happens, at each and every face of the metal, surface of the metal, the highly current will be generated. Okay, the current is nothing but in the form of eddy current. You know that if current has been generated, the electric energy that will be in the form of heat. Okay, so it finally melts. Next, one more example, electric power meters. Okay, power meters. So in the meter bill of your meter board of your home. Okay, electric power meters. So there will be a shiny metal disc in the electric power meter and rotates due to eddy current. In the meter board you can see the rotation of one disc, isn't it? So electric currents are induced in the disc by the magnetic fields produced by sinusoidally varying current in the coil. Okay. So next, we can observe the rotating shiny disc in the power of meter of our house. Okay. These are some applications of the eddy current. Next part, we have seen the advantages, disadvantages. There are certain methods by which we can minimize the losses due to eddy current. Okay, these here in the metallic cores which are used in the devices such as transformer, dynamo, etc. Due to change in the magnetic field, large eddy currents are produced in the core, which causes large amount of heat in the core. Okay. So as a result, there will be a large amount of loss, okay, in terms of heat. If it is a solid core, in the first structure, if it is a solid core, the amount of heat or the on the surface eddy current will be very large, so heat produced will be very large. So here what happens, these cores, for example, if we take a A4 sheet complete bundle, okay, then in that case the eddy current, so on the surface heat produced or on that core will be maximum. Okay, suppose if you remove that bundle and that sheet layer wise. Okay, so this type of laminated core, small thin layers of the metal they will do and arranged one back to another in the parallel manner. So here the eddy current are divided on the each surface. Here each surface of the core will be insulated from the each other and eddy current effect will be reduced. Okay. So these are some concepts regarding the eddy current, that is advantages, disadvantages and minimization of the loss due to eddy current. Okay. Next concept, induction. Okay, so induction is the phenomenon, so EMF will be induced in the one coil due to change in the magnetic flux. Okay, we can see the variation of the current in the same coil or in the neighboring coil. Depending upon this, we can classify the induction into two types. One is self induction, another one is mutual induction. Okay, self induction and the mutual induction. So self induction is the phenomenon in which EMF is induced in a coil due to change in magnetic flux through the coil as a result of variation of current in the same coil. Okay, it's the definition of the self induction. In the same coil magnetic flux varies and in the same coil current will be produced. Next, mutual induction. Mutual induction is the phenomenon in which EMF is induced in one coil due to the variation of current in the neighboring coil. So in mutual induction phenomenon, there will be two neighboring coils. So magnetic flux and EMF will be induced in one coil due to variation of magnetic flux and EMF in the one coil. It gets linked with to its neighboring coil and current produced will be in the another coil. Okay. So let's study regarding the self induction. So consider a coil, okay, whose one end is connected to the battery, another end of the coil is connected to the tap key. Okay, hence it completes the circuit. Okay, consider this figure. Okay, coil connected to a battery through a key. Okay, next what happens if we press this key? current in the coil start to increase. What happens? Current in the coil start to increase. If current increases, magnetic flux linking through the coil also increases. Okay, magnetic flux linking through the coil also increases. Okay, as a result of this, what we can say, EMF will be set up in the coil. So we know that according to Lenz's law, the direction of induced EMF is such that it always opposes the growth of the current in the coil. Okay, when the magnetic flux linked with the coil increases, it further opposes the growth of the current in the coil. Okay, so it delays the current to acquire the maximum value. Okay, so what happens if I release this key? Okay, if I release this key, if this key is open, okay, if the circuit key is released, if key is released, okay, what happens? The current in the coil which has been already generated will start to decrease. Okay, so if current decreases, we know that the magnetic flux linked with the coil also decreases. Okay, magnetic flux linking through the coil also decreases. Next, so here the change in the magnetic flux results in the induced EMF. Okay. Once again, according to Lenz's law, the direction of induced EMF is such that it opposes the decay of current in the coil. Hence, delays the current to acquire minimum or zero value. What happens? If I release this key, okay, magnetic flux decreases by value, nothing but decreases. Okay, if magnetic flux decreases, current which generated also decreases, but it directly doesn't comes to zero. Okay, that is because of Lenz's law. It opposes the decrease of current due to the Lenz's law. Okay, and slowly it comes to zero. Okay, here slowly it comes to zero. The property of the coil which opposes the growth or decay of the current is called as what? Self induction. Okay, so self induction, it always opposes either the growth or decay. Growth in which case? So when the key is pressed, uh, current in the coil start to increase. So as a result, magnetic flux increases. It doesn't reach suddenly the maximum. Okay, so it takes some time due to the opposition, that is because of Lenz's law. Once it reaches the maximum, it has been saturated. Okay, next, what happens if I release the key? Okay, if I release the key, the magnetic flux which link through the coil start to decrease. Okay, start to decrease. If magnetic flux decreases, current through the coil also, EMF generated in the coil also decreases. It suddenly doesn't comes to zero. There will be a certain opposition to the decay of current in the coil, and finally slowly it comes to zero. So this opposing the growth or the decay of the current in the same coil is called as what? Self induction. Here self induction is also known as inertia of electricity. Okay, it is also known as what? Inertia. Okay, it is the physical significance of the self inductance. So inertia means what? Opposes. Okay, in the state of rest. Okay, nothing but, so as it opposes the growth or decay of the current. So inertia of electricity, why it is called so? Because it opposes the growth or decay of the current in the circuit. Okay. So consider a current I is flowing in the coil. If it is a coil, okay, battery, then key, okay. So let's consider current I is flowing in a coil, okay. Next, if current flows, magnetic flux links, okay. It has been found that the magnetic flux linked with the coil is directly proportional to the strength of the current. Pi is directly proportional to I. Okay. How much amount of flux has been created, that much amount of current will be produced. So, directly proportional. The constant term is given by pi is equal to Li. Okay. Pi is equal to Li. So here L is a constant proportionality which is called by the term coefficient of self-induction. What it is called? Coefficient of self-induction, or it is also called as self-inductance. Okay. Coefficient of self-induction or simply self-inductance. Next, we can say L equal to pi, that is self-inductance equal to the magnetic flux. Only one possibility if I is equal to 1. How we can state? Coefficient of self-induction of a coil is defined as the magnetic flux linked with the coil when unit current flows through it, that is L is equal to pi, that is self inductance will be equal to the magnetic flux linked with the coil only when unit current, okay, unit current flows through it. Okay. Next, so we know that according to Faraday's law, E is equal to minus d pi by dt. Okay. E is equal to minus d pi by dt using equation 1. Which is that equation 1 here? One is pi is equal to Li. Substitute that equation, that is in the place of pi, substitute pi equal to Li. Okay. E is equal to minus of d by dt Li. You know that L is a constant term. Only variable is current, that is I. It can be written as E is equal to minus L di by dt. Okay. E is equal to minus L di by dt. Okay. It's the expression of the induced EMF in case of a self-inductor. Okay. Next, if the value, that is di by dt is equal to 1, what we get? L is equal to E. So here the self-induction is equal to the induced EMF when a current, rate of change of current will be decreases in unity. Okay. That is coefficient of self-inductance of a coil is defined as the induced EMF produced in the coil through which rate of decrease of current is unity. So they have considered minus di by dt is equal to what? Minus di by dt is equal to 1. Negative sign indicates what? It decreases the rate of current. Okay. So L is equal to E. So L is equal to pi if current is unity. L is equal to U if rate of change of current is unity and is in the decreasing manner. Okay. What about the SI unit? The SI unit of self-inductance is Henry. Either you can write HENRY, okay, or simply capital H. Here, self-inductance dimensional formula. Okay, the notation of self-inductance is L. Its dimensional formula is given by M1 L square T raised to minus 2 A raised to minus 2. Okay, dimensional formula is M1 L square T raised to minus 2 A raised to minus 2. Okay. So next, inductor, simply which will be a single coil only, self inductor or simply inductor. Okay. An element of an electrical circuit tightly wounded coil of an insulated wire which opposes the change in current flowing through it. So it is a electrical circuit element. Okay. You know the resistor, capacitor. Similarly, if the coils are wounded, okay, which are insulated from each other. So when this inductor connected to any circuit, its main intention is to oppose the change in the current. Okay. So you can see the circuit symbol here. It is the circuit symbol of the inductor. Okay. So in the next class, okay, in the next class we shall study the expression of energy stored in an inductor and also regarding the mutual induction. Okay. Thank you.